In this podcast, we're going to talk about the nature of gases. And in order to talk about the nature of gases, we need to go through the kinetic molecular theory of gases. This is a theory that talks about how gases behave and how they are made up of small particles and things like that. I've broken it down into 5 steps here so you can remember them. Number 1, gas particles are in constant motion, meaning they're always moving pretty fast actually. In fact, if you slow gas particles down to where they stop, we essentially assume they have no volume whatsoever. Number 3, collisions are 100% elastic. What that means is that if a gas particle is traveling about 90 miles per hour and it hits another gas particle or the size of a container, it comes off with a speed of 90 miles per hour, meaning there's no attraction between gas particles and other gas particles or the container. Number 4, kinetic energy of gas particles is directly related to temperature, meaning the higher the temperature, the more kinetic energy it has, and the lower the temperature, the less kinetic energy the gas particle will have. Number 5, lighter particles move more quickly than heavier particles. So if I put a lighter particle into a balloon or something like that, it's going to hit the sides of the container more often than a heavier particle. Here are 4 nice behaviors to remember of gases. Number 1, they have low density. Some are more dense than others, but gases will have a much lower density than solids and liquids. 2 and 3 kind of go together. They're compressible and expandable. We can compress all the air in a room down to the size of a tissue box, and if I release it back out, it will expand. Number 4, they easily go through diffusion and effusion. Most people know about diffusion, but we'll talk about effusion as well. First of all, let's talk about diffusion. Diffusion is when a gas goes from a high concentration to a low concentration and will equally spread out amongst the container it is in. Whether that container is a beaker, a flask, or even a whole room, it'll spread out until it's evenly distributed throughout that container. Effusion, on the other hand, is when particles hit the sides of a container and will eventually slip through tiny holes in the container. You can see on the right there that there is a particle that's escaped out of that hole in that beaker or whatever that is. But that can also happen in a balloon. A balloon has tiny holes on the outside, microscopic, can't even see them. But every once in a while when a particle hits the side of that balloon, a gas particle will escape. It explains why after you blow up a balloon and you come back after several days and the balloon has deflated on its own, generally, there's not a leak in your balloon, it's just the gas particles flowing out the sides through effusion. Graham's rate of diffusion-effusion formula looks like this. The rate of A over rate of B is equal to the square root of the molar masses of B over A. Notice that in the left side, A is on top, and on the right side, A is on bottom. Make sure you remember that if you're doing any calculations. So here's our first problem we're going to try with the Graham's rate of diffusion/effusion. Ammonia has a molar mass of 17.0 grams per mole. Hydrogen chloride has a molar mass of 36.5 grams per mole. How much faster is the diffusion rate of ammonia? So the first thing I notice is that ammonia is lighter than hydrogen chloride, so it will diffuse and effuse faster than hydrogen chloride. As I said, lighter particles move faster than heavier particles. So let's set up our equation. Here's what it looks like. Notice the NH3 or ammonia is actually on the left side on the top, and on the right side it is on the bottom. Okay, so we're going to go ahead and put the molar mass in for hydrogen chloride, which is 36.5 there. And we're going to put in the molar mass for ammonia, which is 17 right there. And we go ahead and take the square root of that answer, and you get 1.47. So ammonia, being the lighter of the two particles, is going to diffuse at 1.47 times faster than hydrogen chloride. So it'll go across the room 1.47 times faster. That also means that it will escape a balloon 1.47 times faster than hydrogen chloride. So a balloon filled with ammonia will deflate 1.47 times faster than a balloon filled with hydrogen chloride. For your second situation, we get a diffusion rate for helium of 14.5 meters per second, and they want to know the molar mass of a substance that diffuses at a rate of 7.1 meters per second in the exact same conditions. So let's fill in our formula here that we have down here. Notice helium is on the top on the left and bottom on the right. The rate is 14.5 and helium's molar mass is about 4.0, so we'll fill those in. And then we put in the rate of the unknown gas, which is 7.1 meters per second. So in order to solve this problem, you'll notice we have a square root on the right side, and the way we get rid of that square root is to square both sides. So we square both sides and the square root will disappear, and we get 4.17 on the left, and we get just molar mass of X over 4 on the right. To solve for that algebraically, we just take 4.17 and multiply it by 4.0, and we get the molar mass of gas X to be 16.7 grams per mole. So hopefully these aren't too hard. Just remember to keep the rate and the molar masses on opposite sides of the fraction on either side of the equation, and you should be set.